In this video, we will examine nomenclature of dienes. To name a diene, one should identify the longest chain that contains both of the double bonds, and that chain is the parent chain. So, name, of course, first the chain as an alkane, then replace suffix a and e of the alkane with suffix diene. Of course, suffix "-ine" means alkene, so diene means it is a diene, two double bonds. Then we should assign two double bonds the lowest possible set of numbers. Finally, number and name the substituents and list substituents in alphabetic order before the name of the parent chain. Here are some simple examples. So 1,4-pentadiene, one very simple diene. This is 2,3-pentadiene. Note that when two double bonds are next to each other, when they are accumulated like this, then we have to indicate middle carbon that is common to both double bonds. We cannot simply draw long lines and assume that one would know that there are two double bonds, because long lines could be simply just one double bond where one made lines longer than usual, or it could be 3 or 4 double bonds that are so-called accumulated, that are next to each other. So this carbon has to be indicated either as symbol C, as in this case, or sometimes we simply place a dot to indicate an atom. And here is a cyclic diene. So this is heptadiene, of course 7-membered ring. So heptadiene is 1,4-heptadiene, because those are the smallest possible numbers. And on carbon 3 we have methyl group, so 3-methyl 1,4-heptadiene. And note that now that we have a diene, we have to include number 1 when numbering double bonds. For ordinary cycloalkenes, we are omitting number 1, but with dienes we have to include number 1. As dienes have double bonds, they exhibit isomerism. So a diene with two double bonds can exhibit isomerism on each of the double bonds. We can designate that isomerism using cis-trans nomenclature, but since this is trivial nomenclature, we usually don't do it anymore. These days we usually rely on EZ nomenclature, and we indicate isomerism of each of the double bonds with EZ nomenclature. Here is one example. This is 2,4-hexadiene, and so before the name we indicate isomerism of each double bond. So double bond 2 is E, and so we indicate that as 2E, and also double bond 4 happens to be E, so this is 2E, 4E, 2,4-hexadiene. So simply we use numbers to indicate isomerism of each double bond. And here would be an example of 2Z, 4Z, 2,4-hexadiene. Note that 2,4-hexadiene has 3 isomers. So we have already seen 2 of them, 2E4E and 2Z4Z. Note that 2E4Z and 2Z4E are identical. And that happens when compound is symmetrical, which means that each of the double bonds has same set of substituents. And you can analyze each double bond, see what are the substituents on it, and you will see that each of the two double bonds has same set of substituents. When that happens, then number of isomers is reduced because 2 of the isomers are identical. EZ is identical to ZE. That brings us to Van 't Hoff rule. Van 't Hoff rule states that maximum number of isomers is 2 to the power of n, where n is number of double bonds. So diene has 2 double bonds, which means that maximum number of isomers is 4. There could be fewer than 4 if there is symmetry present in the molecule. We have seen on the previous example of 2,4-hexadiene that there was symmetry in the molecule because each of the double bonds had the same set of substituents, and that reduced number of isomers from 4 to 3. Here is an example of compound that does not have symmetry and then has all 4 isomers. That's 2,4-heptadiene. So first isomer is 2E4E, then 2Z4Z, obviously different. Now 2E4Z is different from 2Z4E, and you can see that those are obviously two different compounds. So now we have all four isomers. It is possible to have only two isomers even though there are two double bonds present in a molecule, and that's if one double bond does not exhibit isomerism. So here we have example of 1,3-pentadiene. Only double bond 3 exhibits isomerism. Double bond 1 has symmetry. On carbon 1 there are two hydrogens, there are two identical substituents. So double bond 1 does not exhibit isomerism. In that case, we don't need to indicate that designations E and Z refer to double bond 3. Since only one double bond exhibits isomerism, we simply list E or Z, and we know that that refers only to double bond that exhibits isomerism. So these two compounds are designated as E13-pentadiene and Z13-pentadiene. Finally, if both double bonds exhibit symmetry, that means one of the carbons of the double bonds has, of a double bond, particular double bond, has two identical substituents, then there will be no isomers. There will be just one form of that compound. An example is 4-methyl-1,3-pentadiene. So double bond 1 has on carbon 1 two hydrogens, and for that reason it cannot exhibit isomerism. And double bond 3 has on carbon 4 two methyl groups, again two identical groups, so again no isomerism. And therefore there is only one form of this compound. So from these examples you can see that a diene could exist in only one form, or may have two isomers, E and Z, three isomers, EE, ZZ, and then EZ and ZE are identical, or all four isomers are different. So you should be proficient in identifying number of isomers and naming them. And here are some additional examples of nomenclature. So this would be example of 1,4-hexadiene. Dienes, just like any other alkenes, have to have double bonds that are consecutively numbered. So in this case, double bonds must have numbers 1, 2, and 4, 5. So make sure that you don't make mistake of numbering this 1,3-hexadiene. That's a completely different compound. So numbering it clockwise or counterclockwise, this is 1,4-hexadiene. Again, it helps if you write down numbers, and that way you won't make a mistake of assigning non-consecutive numbers to a double bond. Here is what 1,3-hexadiene looks like. And then this is a triene. So this is an extension of what we have learned so far. So compound with two double bonds is diene. With three double bonds it's triene. And of course then longest chain must contain all three double bonds. We number them accordingly. In this case 1, 3, 5. And suffix is triene. Since this is cyclotriene, then it's cyclooctatriene. There are 8 carbons. And on carbon 7 there is a substituent. Of course, double bonds of triene must have the smallest possible set of numbers, which leaves number 7 for chlorine. So 7-chloro, 1,3,5, cyclooctatriene. Finally, some compounds that have two double bonds cannot be named as dienes. That's the case when each of the double bonds belongs to a different chain. Then this compound is named as an alkene. Longest chain, so we look for the longest chain, name that as alkene, and the other double bond is named as substituent. So in this case, the longest chain is cyclic. It has 5 carbons. It's cyclopentene, and substituent is vinyl group. It's in position 3, so 3-vinyl cyclopentene. In this case, we have 2 chains, a ring of 4 carbons, and side chain of 3 carbons. So again, it's a ring that is the longest chain. So it's cyclobutene, and on carbon 1 we have allyl substituent. So this is 1-allyl cyclobutene. And this completes our study of nomenclature of dienes and related compounds. And next we are going to look at reactions of alkenes.